Today's topic at Medical Sciences, we are looking at ultraviolet visible spectroscopy, which we are employing in pharmaceutical chemistry to determine and quantify the presence of molecules within drugs, within drug formulation. We can use it for accurate quantification. And also, we can determine the saturation and the bonding within these components. So we call it UV visible spectroscopy because it utilizes ultraviolet rays together with visible rays, or what we call visible electromagnetic rays. And the UV electromagnetic rays are measured between 200 to 400 nanometers, whereas the visible spectrum is between 400 to 700 nanometers. That is the spectrum, the visible spectrum, or what we call the white light, which is divided into different colors beginning from blue to red. So this one ranges from blue to 700, which is red. And in between there we have different colors. So in summary, UV visible spectroscopy measures between 200 to 700 nanometer wavelength. That is, it's a range of action. And this UV light, it works under the principle of Beer-Lambert's law, whereby the principle we have what we call the Beer's law. And according to Beer's law, he says when using a monochromatic light, when a monochromatic light passes through a colored solution or any solution which is well mixed or homogeneous, they can then, when this monochromatic light is passing through this colored solution, the absorbance is directly proportional, to concentration. Is directly proportional to concentration, or you can call it number of absorbing molecules. Number of absorbing, which is concentration. That is according to Beer's law, which is a German scientist who found out that when a monochromatic light passes through a well-mixed solution, that absorbance is directly proportional to concentration, or what we are calling number of absorbing molecules in the solution, and we can denote it as saying that absorbance is directly proportional to concentration. So this is what we can look at Beer's law. Then according to Lambert's law, for him, he says that when a monochromatic light, if you have a monochromatic light and you pass it through a well-mixed solution containing molecules, that absorbance, the amount of light absorbed, what we are calling absorbance, is directly proportional to the length, or in bracket thickness of the light path. That is according to Lambert's. Lambert's, because begins with L, he was looking at the length. So don't confuse Lambert's law with Beer's law. By knowing that Lambert's, because begins with L, even he's looking at length, which begins with L, or you can call it thickness of the light path. So that is according to Lambert's law, that when a monochromatic light passes through a well-mixed solution, absorbance, or the amount of light absorbed, is directly proportional to the length or thickness of the light path. For example, In summary, we can say that absorbance is directly proportional to length, which we denote B. So length of the light path or thickness, we are denoting letter B. So this is Lambert's laws, this is Beer's. So if we can combine all of them, Beer-Lambert's law, Beer-Lambert's law. So we are going to see that when a monochromatic light, the light has to be monochromatic, passes through a well-mixed solution. You pass it through a well-mixed solution. We are going to see that absorbance, or the amount of light absorbed, absorbance is directly proportional to concentration and the length or thickness of the light path. This is according to Beer-Lambert's law, that when you have a monochromatic light and it passes through a well-mixed solution or a homogeneous mixed solution, the amount of light absorbed is directly proportional to the concentration, what we are calling the number of absorbing molecules, and length of the light path. And we can say that absorbance is directly proportional to CB, concentration and length of the light path. That is according to Beer's law. But in terms of transmittance, if we can define it in terms of transmittance, we normally say if this is a sample holder and here there is a solution which is well mixed, and the light coming, this is the incident light, denoted as I naught, incident light. Some of it is absorbed and another is transmitted. The transmitted one is denoted as I. Then some of it is absorbed. So to measure transmittance is equal to the ratio of the transmitted light, you divide it by the incident light. So transmittance is the ratio of the transmitted light to the incident light. So, and another thing I want you to know that absorbance is inversely proportional to the transmittance. If much of the amount of light is absorbed, less is transmitted. So that's why we say it is inversely. So absorbance is inversely proportional to transmittance. That is what we are trying to mean. So if we have transmittance as the ratio of the transmitted light to the incident light, we can easily use it to get absorbance, whereby absorbance is equal to negative log base 10 of transmittance. But remember, transmittance is equal to the transmitted light divided by the incident light. So absorbance is equal to negative log of the ratio of the transmitted light divided by the incident light. So we are replacing where there is the word transmittance. And at the long run, absorbance is equal to log. If we are removing a negative sign from here, we are going to take the reciprocal of this. And we shall have the incident light on top and the transmitted light down. So this is the formula we can use to relate absorbance with transmittance of light. And another thing, percentage transmittance is equal to transmittance times 100%. That is also another thing we can note in this session. And then lastly, according to this Beer's law, if we remove this constant of proportionality, we are going to say that according to Beer's law, absorbance is equal to, we introduce a constant, epsilon, which is a constant, CB, whereby this constant when you are using a cuvette of 1 centimeter is equal to 1%. This is for 1 centimeter sample holder. The constant is equal to 1%. So this is the formula we can also employ in calculating absorbances of different solutions. Maybe lastly, what we can also talk about is also according to Beer's law, we can also find another formula which says that if I have absorbance of the solution under study and I have a standard, I can easily calculate the concentration, whereby the concentration of the test is equal to absorbance of the test over absorbance of standard, then you multiply by the concentration of the standard. So this one can also be used in calculating concentrations of solution. That's why we say that UV spectroscopy can also be used to determine the quantity or the concentration of molecules within a solution. So that is what we can also employ in this session. So after seeing Beer-Lambert's law and the different formulas we can use, we are going to look at the components of ultraviolet visible spectroscopy, and we shall also end with a summary of the principle of all of the things. And we have here the first thing is the light source, and this light source for the UV light is produced by deuterium, which is an isotope of hydrogen, and this deuterium produces light between 200 to 400 nanometer wavelength, or sometimes 350. Then another one is the visible, which is produced by the tungsten bulb, containing sometimes halogen. And this tungsten bulb produces light between 400 to 750, sometimes even up to 800 nanometer wavelength. So this is the light source we are using. So this light source must come, if we are looking at molecules which absorb light between 200 to 700, this light must have both the UV and the visible. So then when it produces light, these light rays are going to pass through the slit. And this is what we call slit 1. Slit 1 is going to prevent stray light from reaching the monochromata. So this is the prism, or you can call it a monochromata. This is a monochromata, or you can call it a filter, or some books call it a prism. So when light strikes the prism, or what we are calling a monochromata, it is going to split this light into different wavelengths, and it is going only to select the desired wavelength to reach the sample. So it is the one that causes, so this light is no longer made up of much wavelength, but this light is called a monochromatic. This is a monochromatic light. So this monochromatic light is going to pass through slit 2, and the functions of the slit is to prevent stray light from reaching the sample. So in summary, the function of a monochromata is to only select and transmit light of desired wavelength. If we desire to use light at 540, this monochromata is going not to allow any light between 200 to 700, but it's going to select only light at 540. So that is the use of a monochromata, selecting and transmitting only light of desired wavelength, so that it is the one that reaches the sample in the sample holder. So this is the sample holder, and this sample holder, you can call it a cuvette, and these cuvettes are always 1 centimeter long. It is standard 1 centimeter. So when the monochromatic light reaches in the sample, or reaches on the molecules depending on their concentration, these molecules in the sample are going, so this is the sample. So when this monochromatic light reaches there, these molecules are going to absorb light. And if I can illustrate it here, that the atoms or molecules in the sample are going to absorb light. This is the lower energy level. Then we're going to have, this is the higher energy level. So when the light strikes the molecules in a sample or atoms, the atoms are going to absorb heat, to absorb light. They absorb light, and after absorbing light, they become excited. They become excited, and when they become excited, they jump. They jump. After excitation, they jump from lower energy level to higher energy level. And after jumping, they are going to jump at a higher energy level, and where at a higher energy level they are unstable. They are unstable, and because they are unstable, they have to come back to the lower energy level to gain stability. Because at lower energy level, they are bonding. They are bonding, that's why they are stable. But when they absorb light, they become excited and they lose the bonding molecule and jump to higher energy level, whereby at higher energy level they are anti-bonding. Here they are anti-bonding. So that's why they are unstable. And because they are anti-bonding, they must come back to the ground state or to the lower energy level to gain stability. They have to come back to gain stability. And as they are coming back to bond again to be stable, they emit photons of light. They emit photons of light. And these photons of light emitted, they depend on the number of molecules in the sample and even the length of the sample holder. So we are going to see that this light, which is depending on the concentration and the length of the light path, is going to be transmitted to the photodetector. So it is transmitted to the photodetector. This is the photodetector, and the common type of photodetector used is the photomultiplier tube. Photomultiplier tube has ability to amplify. It contains an amplifier that if it gets a low intensity transmitted light, it is able to amplify and you get the results on the readout. So this is the reader or the galvanometer. This is the readout, or you can call it a galvanometer. So it is the one that displays the intensity. But what is the function of the photodetector? The photodetector, its role that when this light which is transmitted strikes the photodetector, the light energy is converted to electric. So the role of the photodetector is to convert light energy into electric energy, which can display signals on the galvanometer. And the signals or the readout which are displayed depends on the number of molecules and the length of the light path, and it is directly proportional to the number of molecules within the sample. So this is the components and at the same time the principle. So if they ask you the principle of UV spectroscopy, you first tell us that it works under the principle of Beer-Lambert's law, which states that when a monochromatic light passes through, when it passes through a colored solution, the number of or the amount of light absorbed is directly proportional to concentration and length of the light path. Then you tell us that when light from the light source is produced, it passes through the slit one, which prevents stray light from reaching the monochromata. And when the light reaches on the monochromata selects light of desired wavelength and transmits only this light and stops others from being transmitted, hence producing a monochromatic light. And when this monochromatic light reaches the sample in the sample holder, the molecules within the sample are going to absorb this light energy and they become excited. And when they become excited, the molecules within the solution, they are able to jump from lower energy level to higher energy level. But at higher energy level, they are antibonding. So they are not stable. They have to come back to gain stability, to bond again. And when they are coming back to gain stability, that's when they emit photons of light. These photons of light are equivalent to the amount of light which was absorbed, which depends on the number of absorbing molecules in the sample. And this light goes to the photodetector, which is converted into electric energy, and the electric energy is signaled in the form of a graph on the readout, and you're able to quantify the molecules within the component. So that is the principle of UV spectroscopy. And how can we measure the energy? Here the energy absorbed is E0, and at higher energy level it is E1. So to get the quantum of light, energy is equal to E1 minus E0. So this is how you can determine the energy or the quantum of light absorbed by these molecules at this level. So this is the principle we can discuss with you of UV spectroscopy. And this UV spectroscopy is affected by factors. So the factors that affect this spectroscopy, one include pH of the solution, can affect. The second one is the number of bonds, whereby like alkanes absorb differently from alkenes and alkynes. Then another one is the presence of chromophores like benzene, which affect the wavelength of light. The chromophores do not absorb light, but they affect the wavelength to be transmitted. An example is the benzene ring acting as a chromophore. Chromophore meaning these are groups which are colored. But these chromophores, sometimes they can also have oxochromes. These oxochromes are chromophoric groups. They are attached on the chromophores. For them, they don't absorb light, but they affect the wavelength. And some of the oxochromes include like functional groups, like sulfhydryl, like nitrile, like amine group. All these are acting as the oxochromes, which affect the amount of light absorbed at different wavelengths. If we can demonstrate a small graph here, if we have a graph here, we're going to see that these oxochromes and chromophores, if this is the wavelength, some of them can cause hyperchromic, others can cause hypochromic, others can affect by causing bathochromic, that is whereby it is absorbed towards the red side, the red color, which is the last one with the longest wavelength. Then another one can be affected by hypsochromic. This is hypsochromic, whereby this one is being absorbed at the blue extreme at 400. That is short wavelength. So these oxochromes and chromophores affect either by increasing the wavelength or decreasing the wavelength, or it can increase the amplitude of the wavelength or decrease the amplitude. That is what we can look at. So this is what we can discuss with you in this session on UV visible spectroscopy. More still coming. Stay tuned. Make sure you subscribe if you haven't, and like the video. So please remember Beer-Lambert's law, and remember that UV visible measures between 200 to 700 nanometer wavelength, and we have seen how to apply the Beer-Lambert's law, and we have seen different components of UV spectrophotometer, which we have seen light source, deuterium for between 200 to 400 nanometer, and then the tungsten or halogen between 400 to 750. Then we have seen the function of a monochromata is to select only light of desired wavelength. Then when the monochromatic light reaches in the molecules, they use what we call electronic transition, whereby electrons along the orbital, they are able to become excited and jump from lower energy level to higher energy level. And as they are coming back, they emit photons of light, which are the same as the number of light absorbed when they were going to the excitation state. And we have seen the function of a photodetector is to convert light into electric energy. Thank you so much for learning with us. May God bless you.